Hello, my name is Marco Bohnhoff. I'm based at GFZ in Potsdam, which is the National Lab for Solid Earth Geoscience in Germany. And there I'm running a team aiming at understanding and deciphering deformation processes across the entire possible scale. And that is from the microscale in the lab, across the mesoscale, which is mainly geological reservoirs, and then all the way up to the field scale, which is along active tectonic plate boundaries. On November 9, 1989, when the Berlin Wall fell, I was just finishing school and started an apprenticeship in Hamburg. And at that time, my world ended just 50 kilometers east of my home. What I did right afterwards was commuting to Berlin. And that is actually what I'm still doing, commuting between my hood then, during childhood in Hamburg, and my current hood, which now is in Berlin. Well, I went through quite some evolution, transforming from my wish to become a bank account manager when I was a child, then transferring to the wish to become an electrical engineer in high school. And finally, when I finished school, I ended up with the wish to become a seismologist. So basically, I'm happy that school did not end earlier for me. My research team aims at contributing to deciphering processes governing the earthquake machine. We know that the current growth of population centers co-located with active tectonic plate boundaries face an ever-increasing seismic hazard and risk. And while we know that individual earthquakes are currently not possible to be predicted, and maybe cannot be predicted in general in a deterministic way, here in the lab, with making tests on these kinds of rock specimens under controlled conditions and with the option to repeat the experiments, we can learn about the processes that govern earthquakes. And actually, we do observe earthquake preparation processes here in the lab. And this knowledge gained here in the lab can then be transferred onto the field scale and to the reservoir scale, where we can apply these towards improved operational earthquake forecasting systems with the aim to mitigate man-made, so-called induced earthquakes in reservoirs, and with the aim to extend warning times for upcoming larger earthquakes at the plate scale. So in the laboratory, at the microscale, the big advantage is we can entirely control the experiments, we can change the boundary conditions, and we can repeat the experiments within hours. These processes in nature take 100 or more years, and that is time we don't have. So what you see here is sort of the mesoscale. That represents the geological reservoir, where we can still use instrumentation like in the lab. So we put our instruments, our monitoring devices here in drill holes. And then we can inject fluid, which represents the stimulation of reservoirs to enhance the production of, for example, geothermal energy. And we can then apply the methods that we developed in the lab onto the mesoscale in reservoirs. And we actually succeeded in developing near real-time monitoring systems that allow us to mitigate induced seismicity, which is anthropogenic earthquakes, if you want. And this actually is the crucial step towards finally controlling these kinds of seismic activity. And again, this is done by looking at very small detection threshold at the tiny little events that typically precede the larger ones, which is key to success for then improving earthquake forecasting systems at the plate tectonic scale. So we now have great confidence in the, let's call it, earthquake preparation processes that I've shown you in the laboratory, where we have them under controlled boundary conditions. We have sort of semi-control on these processes on the geological reservoir scale. And now the final step will be to extrapolate the same technique and the monitoring approach also to the field scale. This is the map of Turkey with a tectonic hotspot in the Marmara Sea where the Istanbul megacity is co-located with a fault segment that is overdue for a large earthquake. And we now have started to implement the monitoring technology there in the frame of a plate boundary observatory initiative. And first results actually show that moderate earthquakes that have occurred in recent time show the same type of preparation processes as we saw in the lab and as we know that they occur in the reservoir. And if we could observe this in a systematic way, these could then be transferred to an improved operational earthquake forecasting system, which would allow to extend warning time from seconds to minutes or even more. And this would be a big step forwards towards eventually warning population in advance of upcoming large earthquakes. From research conducted by my team in Potsdam, the society can benefit in two ways. First of all, we contribute towards a safer exploitation of geothermal reservoirs by supporting a mitigation of man-made earthquakes. Second, we contribute towards an improved warning time for large earthquakes by applying methods that allow to detect preparation processes of larger earthquakes, not only in the lab, where we know we can do it, but now also on the field scale. And this will help mitigating seismic risk assessment and risk mitigation for large metropolitan regions. Where we stand now in seismology is certainly not the end of the road. There is a strong discussion in the room elaborating the role of so-called slow deformation. Slow deformation means that energy stored in the earth crust that is typically released instantaneously and fast in earthquakes can also be released slowly along a longer period of time, thereby not posing any seismic hazard or risk. We currently install these kinds of investigations in the lab, and we actually start to also be able to observe these slow processes. And the long-term goal, which is not yet existing, would be to find the ultimate switch to change from fast to slow deformation, thereby systematically avoiding seismic risk due to earthquakes.